Again, as mentioned, I'm Ben Amaskarian. You could call me Ben. And my office is in the ECS 221J. The office number is 651-5248. If I'm in the office, I usually answer the calls. If I'm in the class or in a meeting, you can reach me over the phone. So please email me. This is my email, bskarian@dawoodtamu.edu. And give it, please, 24 hours. I get like maybe 100 email a day. So it takes a little bit of time for me to answer those questions. I've tried to answer faster. So this semester, but especially during the weekends, just please give it like 24 hours until you get a reply. And if it's an emergency, just you can stop by my office at any time or at my office hours. I'm in my office from Monday, Tuesday, from 3 to 5 p.m. or any other time. You can email me and set up an appointment. Or if you just want to meet me, most of the times I'm in my office. Even if the doors close, I may be in the office, just knock on the door and I will try to help you out. This class, we don't have any required textbooks. We have these two recommended textbooks. I would provide you with all the materials that you need for this class, so you don't have to buy any books. And the only requirement for on the exam would be maybe a simple calculator. On the exams, I usually provide all the necessary equations as well. And usually the exam in each exam I provide all the materials that you may need, all the equations and so on. And if there's like a table that needed, for example, to measuring reactive power, so on, that would also be provided. So in this course, we would study the concepts of measurements, analog measurement tools, digital measurement tools, and also accuracy, error, specificity, sensitivity, resolution, and so on. Other concepts like absolute error and drift, and so on. And we will also go through some mechanics of these analog instruments, but our focus would be mainly on digital instruments. We'll continue with power measurements, three-phase power measurements using 1 watt meter, 2 watt meter, and 3 watt meter methods, measuring active, reactive, and apparent power as well. And Wheatstone bridge is a part of the class as well for measuring current or voltage or a resistance, measuring different capacitors and inductors using different types of bridges like Maxwell bridge and Hayes bridge. And finally, we will go through some biosensors, different types of sensors, and so on, such as radars, collision sensors that are used in cars for deploying airbags, LiDARs, and ultrasound sensors as well, ultrasonic sensors as well. You're already familiar with the program learning outcomes. I'm not going to go through it. Just please read the syllabus. And the important part here is the course requirements and evaluation. The homeworks would be 5%. Project, the final project, which is a hands-on build. You have to build a project, and that will be 10%. You will be asked to build any type of circuit that, as long as it has a measurement tool like a distance measurement system, a voltmeter, ammeter, anything that measures a quantity, physical quantity, would be accepted. And then student involvement, which are the Kahoot quizzes. which acts both as attendance and also it's going to be a part of quiz. 30% of these quizzes are for just attendance, and it's randomly. You may have these quizzes every week or every other weekend or so on. There will be 2 exams, 25% for each midterm exam, and there will be a final comprehensive exam that covers all the materials, and that would be 30%. If you build a project with a PCB board, and I'll put out the tutorials and everything, it's pretty simple, you would get extra bonus points depending on how sophisticated it is. Maybe even the project score would go up to 20%. But if you build it using breadboards, it's the maximum of that 10%. Again, but if you go beyond and build it with a PCB board, you would get bonus points. Now for homework assignments, usually I would give a week, sometimes 10 days to turn in those homeworks. This semester, I'm going to give much more homeworks based on my experience and the feedback that I got from students. You're going to have more homework this semester if you had any other courses with me compared to the previous homework semesters. And unless you have there's a good excuse, I would not extend the deadline for the homework or quiz, especially if you're an online student. There would be no excuses for not taking the quiz or the exams on time, unless there is a family emergency, illness, or something like that, and you have the proper documentation for that sent to me before. Unless you have those for the project, for the homework, I had a lot of problem with the students turning in their homeworks and projects late the last semester, and I couldn't post the grades on time because I had a few students missing their exams or projects. So even in a minute after the deadline, I would not accept any submissions, homework submissions. So these are the homework policy. The only thing that if you don't have an engineering paper, it's okay, just use normal paper for submitting, but it must be submitted in PDF format, and I have to be able to read it. So if it's sloppy work or something, if I can't read it, I can't grade it. And if you're writing on your tablet or anything, just screenshot of that will be okay. Again, no makeup quiz or exams would be accepted. And one thing that is very important, and I had problems with in the previous semesters, is the use of generative AI, ChatGPT and Gemini and so on. The policy for this class is that AI is strictly prohibited. And if you use AI for any of your homework assignments, especially in your exam, you would be given a 0 for that homework. I would encourage that you sit with your friends and try to solve a problem. That is okay with me on your homeworks, not to copy each other, but just sitting in a group and trying to solve problems. That is acceptable for homeworks only, but again, no use of generative AI and so on. And again, if any of your project is using generative AI, you would be given a 0 for that project, for the report, for your homework, especially the exams, and so on. And another thing that I wanted to mention is that the reason is that I want you to build a problem-solving skill here. I forget most equations that I had from example for microwave antenna that I taught like 10 years ago, 5 years ago. I'll guarantee you would forget like 80-90% of equations that you learn during your bachelor degrees, but the concepts would stay with you. Okay, So I want you to learn the concepts. If I tell you what error means, you don't need to remember how to calculate error, but you need to know what error means and how you can measure it in a real world scenario. So critical thinking, problem solving, engineering is not like studying history or philosophy that you can memorize anything. You need to try to learn to solve these problems, even if I know it's frustrating. Maybe a question would take 2 hours to solve, but until you solve them, you're not going to build that neurological path, and you're not going to, memorize it. And the ones that you learn through frustration, it's going to stay with you forever. Again, that's the reason I usually provide the equations. But and in the FE exam, for example, you will be given all the equations that you need. But if you don't know how to use them, how to solve a problem, it's useless. So again, no generative AI. Again, exams, especially if I see especially for online students, if I realize that a student has been copying other students, any, you know, if I see any suspicious activity, it would be an automatic 0. And I also included the academic integrity clause here. And the other statements that we have. And please read the safety instructions as well. The tentative calendar for this semester, we will start with the introduction to measurement and instrumentation. Week 2 will be classification of analog instruments, errors in ammeters and voltmeters, measurement of power and energy. Then it will be a review for exam number 1 and exam number 1. And then it will be dynamometers and the different types of watt meters, measurements and powers in 3-phase, measuring reactive real power, power factor, and so on. Maximum demand indicator, power factor, as I mentioned. And then it will be a review for exam number 2 and then exam number 2 for week 12. And then it will be measurement of inductance and capacitance using different types of bridges. Finally, we would have principle of DC potentiometers and AC potentiometers and biosensors and sensors if we have time in week 15. During the class, at any point, if you have questions, just please stop me and I will try to explain it in a different way. I'm comfortable with explaining things 100 times. Maybe don't be shy if you have any questions. Maybe your question would be your friend's question as well. Please go ahead and ask any questions if you have. If you don't understand my accent or I'm going too fast, just please tell me and I will try to explain it again in a different way or slower or using a different, for example, if you don't understand a graph, I can use a different graph or a different system to present it. All the course materials has been already uploaded for all the course lectures. I haven't uploaded the homeworks or the videos yet, but I would put a link for the videos from the previous semester, and for the online students, each week I would post the YouTube link for that week as well. But I will give you access to the previous semester's videos as well. And also I would add some additional resources if you want to do your project using simulation tools like EasyEDA, Flux, and so on, and you want to build a PCB for that, I would also include that as well. During the class, this class doesn't require a lab, but from the beginning in 21, I started providing labs for this class because I think it provides a great value. You would have hands-on experience on measurement tools. For example, if you want to measure a 3-phase voltage using 2 watt meters or a to or the reactive power and power factor and so on. And also in the lab, you would spend a week or two maybe learning about the contactors, three-phase contactors, the control systems for these contactors, a star delta motor, how we go from star delta, or left turn, right turn motor, how we go from left turn, right turn, and so on. Do you have any questions about the syllabus? Okay. So again, let's start with the class. Measurements and instrumentation. As mentioned, our focus would be mainly, again, on digital instrumentation, and the measurements is the same for measuring error and accuracy and so on. So why do we need to measure different things? And obviously, we want to, if you want to build something, you need measurements on the weights and the dimensions and so on. We have measurements in different categories. We want to measure weight, length, temperature, speed, and so on. There are different ways to do measurements. We can do mechanical. We have mechanical systems, and we have electrical and electromechanical systems as well. I'm going to go through some mechanical systems. So, for example, if you want to measure the temperature, one way to measure temperature is you can use a liquid, and we know that the materials expand when they heat. So we can put it in a very thin tube, and we would have a reservoir at the bottom. If you heat it up, then it's going to expand. So it's going to show you a higher number, and you can put tick marks, and you can measure the different temperatures. Do you know how we calibrate this type of temperature measurement systems? How do we know where it is 0 and where it is 100? So you can put mercury, for example, in this liquid metal, and but how much should I put in? If I put too much in, when it's at 0 degrees, it's going to be more than 0. It's going to show us 2 or 3 degrees. How do we calibrate this? How do I know where is 100, where is 0? Imagine it doesn't have any numbers on it. I just give you this tube with a very thin tube with a reservoir at the end. Doesn't have any of these numbers. And I ask you to just give me a second. There's a problem with the cable here. Yes, how do they calibrate? I'm sorry? Yes, we use water, but that's a great point. Thank you. And we know that the water freezes at 0 degrees. By the way, this is Celsius, not Fahrenheit. And it boils at 100 degrees. So we can use water, put it in water. But the problem with water is if the water has any impurity, if we add salt to it, then the freezing temperature drops below 0. So we need, first of all, we need pure water, distilled water. Shouldn't have any contamination or so on. And the other problem with water or any liquid is that, yes, perfect pressure. If you boil water in Amarillo, the boiling point would be different when you boil it in Houston. So the water boiling point is 100 degrees Celsius, but it's at sea level. And obviously at Amarillo, we are way above sea level, or in Colorado. So you need to have this at the sea level. You have to have pure water, and then you boil it. You would find 100 when it starts boiling, and you would freeze it down to 0 degrees. That would be your freezing point, which is 0 degrees. And then you would divide it to 100, equal spaces, and then each space would be 1 degrees. And in the factory, obviously, you can't take this to a seaside. We have tools that are accurately, and we have this for all measurement tools, which are calibrated. And then the only thing that we would do is usually we would compare these to those accurate tools. So if you have a digital humidity sensor or a digital temperature sensor, we have special tools which are very expensive, are calibrated, and the only thing that you would compare those and to those calibrated tools. Now, a different way to measure temperature is using two metals. You've already seen these in if you have a barbecue, grill. You've already seen this, or a thermometer that measures the temperature inside a meat when you want to, make a steak or something. And the way that it works, we have two different types of metals, and these two metals have different properties. And when you heat them, they expand differently. And you would connect them. Usually, you would glue them or punch them or weld them together. And if one side expands greater than the other, it starts creating a spiral shape. And using that spiral shape, you can connect it again to a needle, and you can put tick marks, and you can measure different temperatures. The good thing about this type of temperature measurement systems and thermometers is that these are very durable, work in extreme high temperature. The other one only goes up to 100 degrees, so you can't use a liquid one, mercury one, for if you want to measure the grill temperature. It's gonna break. Mercury has a boiling temperature as well, a little bit higher than 100 degrees, but when it boils, it becomes gas, and it's gonna expand, and it's gonna explode. But this one, it's safer, it's much more robust, and it's very cheap. And actually, if you have an old water boiler at your home, you may have one of these on them as well. But the downside is that after a while, they will lose their property and the accuracy. It's going to shift. It's going to create a little bit of error. And the other problem is, for extreme high temperatures, you can't use it. So anything that is higher than, let's say, 500-600 degrees Fahrenheit, it's going to permanently damage these. And obviously, these have boiling, melting points as well. So if it melts, you can't use them anymore. Or if it breaks, and they break a lot as well. But again, it's cheap, and they are very reliable. Another example is for measuring speed. How do we measure speed in a car? We count the number of rotations that the tire has, the wheel has, and we can measure the speed using that. There are different methods. They are like older cars, they are mechanical. So there was a direct, coil wire coming from the differential or the gearbox to the speedometer. And when that moved, it actually, I don't know, have you seen these springs that they use for opening the drainage or something? Have you seen those coil springs that they use for opening? If you had a clock's, yes, those snakes. Thank you. It's exactly the same thing. I remember I had those old BMWs. I used to race a lot. I was like, and I had those old BMWs, and if you wanted to change the speedometer, you would, and the whole speedometer was outside. You would just put these electric screwdrivers, drills, and you would just connect it, and you could wind them up or wind them down. It was as easy as that. And then it came these digital ones after that, because easily you can change it if you wanted. Those mechanical ones, you can even, you would put little bit of, magnet or a stick on the one side, and you could play with the speed. So you would think that you're going like 200 miles an hour or something like that. Easy to manipulate. But these the digital ones, you can't do that anymore. And one thing that I remember, and I used to have a 4Runner, and I used to go off-road. So I put these huge tires on them. And each time if you increase the number of tire, the diameter of the tire, the speedometer gets out of calibration. And I will give you an example. If you have a small wheel like this, and this wheel, I'm done doing it in metric system. If if one rotation of this wheel goes from here to here, and this is 1 meter. If I have a bigger tire, now one rotation of this is 1.5 meter. Okay. And I measure one total rotation. And the sensor is usually connected to the differential or the shaft. So this only measures one rotation. So this thinks it's 1 meter, for example, per second. This would be 1.5 meter per second. But the sensor is still reading 1 meter per second. So I was going down the road and I thought I'm going like 60 miles per hour. But since I changed the tires, I was actually going like 65, 70. And yeah, I was stopped by the police, and I thought I'm going at the speed limit, but actually I was actually going was higher than the speed limit. So when you change the tires and put like bigger tires or rims, you have to recalibrate the system because you're going faster than you expected. Now, how does a digital system measure that? Usually on the shaft or a differential. Usually it's on the differential or the gearbox. They have this DC motor, DC generator. The faster that the generator goes, the shaft goes, the motor spins faster and it generates a higher voltage. And then you can measure the speed. And the duration you can multiply, like if it's going 20 miles per hour in the time, and you can get the amount of distance that you went as well. These systems are much more accurate. Again, if you want to calibrate them, it's much more easier to calibrate these compared to the mechanical ones. It's just a line of programming. You can reprogram it by reprogramming the ECU of the vehicle. And again, the faster the differential spins, you're going to generate higher voltage or current. Sometimes they measure current, and you can measure the distance that traveled and also the speed. Another example of these, I don't know, have you seen these crank lights? You just spin them. It's technically a spot generator in here, and the faster that you spin it, you're going to generate higher voltage. They have a small battery as well, so when you spin this, you turn the crank, you're generating energy, and it's going through the battery, and you're charging the battery. It's the same principle. Now, to measure the electric voltage, so imagine that you have a generator, small DC generator over there or AC generator, but now you want to measure the voltage because that voltage gives you the speed. What you can do is you can use a voltmeter like this. And the way a voltmeter works is that this is a electromechanical voltmeter, by the way. Nowadays we have digital ones, especially in cars. The cars are now like a smartphone. A smartphone is not that powerful, actually. It's like a computer on wheels. Some of these new cars, which have self-driving or lane keep assist, they are scanning the road 200 times per second. They have very sophisticated image processing systems to find the lines. So you usually have the camera, they would find the line and then keep you in the center. Or they have powerful what we call millimeter wave radars. And those radars measure the distance between the car and the car in front of you. And if you have adaptive cruise control, they would slow down or accelerate if the car in front of you slow down, accelerate. And it does those measurements 2,000 to 3,000 times per second. So they have very powerful processing, and they have usually 2 or 3 backups. Because imagine if that radar, the ECU goes off, and you're going to crash. And that is controlling your acceleration, your brakes, and also if you have an ESP, what we call, it has control on each wheel separately. So if you're going on a corner or you're turning, it will put more power on some wheels and less. And if you're in a slippery situation, it will put brakes individually on each wheel. And it does that 2,000-3,000 times per second by measuring the speed of each wheel. So these are become very, very complicated systems. Let me give you an example. Mercedes-Benz right now, an S-Class, as I remember, it has like 300 miles of wiring in a car. Single car, you have 300 miles of wiring. And they have up to 30 different computers. So you have one computer for the ABS, one computer for the airbags, and so on. The lighting, infotainment system. Now they are combining them. Like the Rivian used to have, I think, 20-something computers. Now it has 7. They're combining them. And nowadays with the self-driving NVIDIA, they have 2 or 3 NVIDIAs in them just for the self-driving itself. Like 10 years ago, you could easily repair your car at your garage. Now they're becoming almost impossible. Very complicated systems. And but for mechanical systems, and I would bring one in the next class, you have a coil. This is just to measure voltage. And from electromagnetics, you know that if you put a current through a coil or voltage applied to a coil, that coil creates a magnetic field. And if you have a needle that has, for example, an iron metal on it, let me draw it here. Just give me 1 second. You have this needle. You give this a magnetic field. It's going to attract this needle, and you're going to move this. So the higher the voltage you put in the system, you're going to have a higher magnetic field. I'm going to draw the magnetic fields with the red ones. And you're going to have a more power or a stronger field to attract this needle. But there are significant drawbacks with the system. Can you tell me what are the problems with this mechanical system to measure voltage? Again, higher voltage gives us a higher magnetic field, and you got to have more movements in the system. But there are some problems with this system. Can you tell me some of the problems with this system? Think of some of the problems that this system may have.
Spring wearing out.
Perfect. Great. The spring, this is a mechanical system. The spring will wear out. If you pull the spring like 2,000 times, it's going to lose its, it won't go back to this original part. So what you have to do is every like 2 or 3 months, you have to recalibrate this. There is a recalibration, screw at the back, and you have to do that. So that's one problem. Thank you. Can someone else think of another problem that this may have? It's not super accurate. Perfect. It's not accurate as a digital system. You may have errors, and I'll show you some errors that we're going to have. There's another big problem as well. Imagine if this is in your car, and this is, instead of voltage, it's actually showing, and it's exactly the same thing. It's showing your speed. This is your speedometer. What problems this may have if this is in your vehicle, and this vehicle has a lot of vibration. Maybe you're going off-road. So what happens if you have a lot of vibration in this system? You're going to have, it's going to damage the spring, the wire coil. So a lot of problems that you're going to have. So these systems are very sensitive to impact and mechanical forces. So you have to design them in a way very steady that would endure like 200,000 miles, and it still works. And you can't open your speedometer every 100,000 miles and recalibrate it. So that's the reason these older ones, sometimes you even see, I don't know if you drove these older cars, you see the needle is just vibrating all the time, or you would see that it suddenly drops or goes up because, again, vibration has a lot of effect on the spring, on the coil. They have small bearings in the middle, a lot of things. And a small hack that I wanted to actually tell you is that there's a very easy way to hack this system. Okay, and this is the same system that they're using. Technically, this is the same, and I'll show you how it works on these older watt meters that you have at your home. Okay, don't tell everyone that I showed you this. This is an easy way to hack this. And what is this? Do you think? Imagine that you have a car and you want to freeze the speedometer. You don't want it to show the odometer to show any mileage on it. Perfect. Put a magnet on it. Put a big magnet on it, and it's going to stop moving. Okay, so put big magnet on it, or at the back. Usually, I remember you just put like these small matches on the back side, and it will block the movement, and it's not going to stop moving. So it's going to be that easy to actually manipulate and stop it from moving. So what happens is that if you have a magnetic field, strong magnetic field, it's going to stop moving this. So if you have a very sensitive situation, you want to measure, I don't know, the airflow or something, and you want to use a gauge like this, and that is in a strong magnetic field, you're going to have problem. For example, this is just an example of using these voltmeters. Now, this is another example of a mechanical system for measurement. This is for making a scale with rubber band. Again, you can put a paper clip, a rubber band, and if you put the weight on it, it's going to expand and you can measure the weight. Again, for this, you would need a system to calibrate. And how do we calibrate weight? We actually measure weights in sometimes, most of the times, we measure weights and we have calibration system using water. 1 liter of water is 1 kilogram. So that's the reason. So 100 milligram, 1,000 milligrams is going to be 1,000 cc or 1 liter. So 1 cc is 1 milligram as well. That's the reason. That's how we do it in metric system. I don't know how do we do it in pound. So kilogram is like that. 1,000 grams is.
Is it important to use distilled water in this?
Yes. Distilled water must be, and all of these are measured, by the way, in room temperature. Thank you. Because if it's not in room temperature, it may expand a little bit, but 1 liter is 1 kilogram. And then they measure it, and so half a meter will be 500 grams and so on. But the thing is, again, they have these weights. I don't know if you've seen these weight measurement systems that they have, that they put these small weights on it. Have you seen these analog ones that the old, in the farms they used to measure the cattle weight? Or have you seen these, I don't know, scales that they use, mechanical ones? Actually, there's still some doctors' offices, they still use these, mechanical. Those weights are actually very, very accurate. And the way that they calibrate them, as I mentioned, is using a very accurate calibration system in the factory. Another way is to use a spring, and it's the same principle. We can place a plate on it and use the spring. The problem with the rubber and spring, again, after some time, the spring is going to, or the rubber is going to lose its property, and you're going to have an inaccurate measurement. So you have to calibrate it again every few months or after certain measurements. Now, obviously, for measuring very large objects, we can't sometimes use these mechanical tools. For very small objects, you're already familiar with micrometers for measuring small items. If you want to measure the diameter or spacing between something. For measuring very high objects like a mountain, there are different ways you can measure the shadow, and there are different ways, again, measuring, or you can use an ultrasonic system or have someone at the top of the mountain, and you have a transmitter or receiver. You measure, example, how long it takes for voice to go from the top to the bottom. Then you would measure that distance, and you have the horizontal measurement, and then you can measure the height. But now, obviously, we don't do it this way. We are using these, what we call the RTK GPS. And if you want, I would explain what RTK GPS means and what's the difference between that. And the accuracy of those is around centimeters and sometimes millimeters if you have a very powerful system. Now, to measure the distance, you can use a wheel again. You can put a mark on the edge of the wheel so that you can count its rotation. And for example, if you have let's do a small example. What if the radius here is 20 centimeters? And this goes for 5 rotations. Actually, this is interesting. So imagine the radius on this wheel is 20 centimeters. And from here to here, we have 5 rotations. What is the distance between A and B? I'll give you a few minutes to think on this.
Have one of these.
Okay, what is the answer? I'm sorry, 2 pi meters. Okay, so 2 pi r is the circumference of the circle. And what is r? It's 20. So 2 pi r would be 125.6 centimeters, by the way. And if you multiply by 5, it's going to be 700. I haven't done it this part yet. I did the first one. It's 628. Yes, centimeters. 6.28 meters. Did you get the same result? Okay. Okay. Thanks. Okay, perfect. Now, another type of measurement, if we want to measure rotational speed, we can connect a ball with a rope, and the higher that it spins, the faster that it spins, you're gonna get it higher. And measuring this angle, you can measure the rotational speed, or measuring this height, you can measure rotational speed. Again, the faster a wheel spins, the higher the voltage it would generate. This is one way if you connect it to a DC generator. Usually if we have for example, in a power plant, when we want to measure the rotational speed of the generator and the turbine, we don't use these methods. We can use actually see the output voltage of the generator and measure that. But another way to measure that, especially if you want to measure the rotational speed of a turbine, is usually they would put a line on the turbine shaft, and there is a laser receiver and transmitter that transmits light, and each time that it passes, that's one rotation. So that what we call the optical rotational speed measurements. Another way that I've seen is these small DC motors that have a small wheel on them, and you can mechanically connect this to the rotational, like the flywheel or something in a car, and you can measure the speed by measuring the voltage that produces. So the concepts of measurements, we have the measurements, instrumentation, error in measurements, calibration, and standards that we have. What does measurement mean? Measurement is a comparison between a standard and what we want to measure. The measurand. We have two quantities that are compared. The result is expressed in numerical values. Basic requirements for a meaningful measurement. The standard used for comparison purposes must be accurately defined and should be commonly accepted. The apparatus used and the method adopted must be provable or verifiable. Again, you can read faster than me. What does that mean? We have standard, global standards. We have global standards, and then we have US standards. So anything that we use is different from the other parts of the world. But they must be accepted. So for example, the metric system, volts, currents, how much is 1 volt? How much is 1 amp? How do we measure that? How much is 1 kilograms? And it must be unified and repeatable and verifiable. So if you take 1 kilogram from here, take it to Singapore or Hong Kong or Denmark, all of that would be the same if you measure it there as well. And so these standards, again, and we have different standards, as mentioned. In the US, as you know, we have pound, and other parts of the world, they use grams and kilograms. For scientific purposes, we almost never use pounds or gallons. We go with the metric system. So two major functions of all branches of engineering. We have design of equipment and processes. We have proper operation and maintenance of equipment and processes. And I'll give you a little bit of example of these later on. We have two different types of measurement methods. We have the direct method and the indirect methods. So in direct methods, the unknown quantity called the measurand is directly compared against a standard. In the indirect method, the measurements by direct methods are not always possible, feasible, and practicable. In engineering applications, measurement systems are used which require need of indirect methods for measurement purposes. And I would give you some examples of these later on as well. Do you want me to? This is already online, so you have all of these again. No, if you want to take notes, but just let me know. I'll slow down a little bit. So measurements involve the use of instruments as a physical means of determining quantities or variables. Because of modular nature of the element within it, it is common to refer the measuring instrument as a measurement system. The evolution of instruments, the first instruments that we had were all mechanical. Then we came along the electrical measurement systems, and finally the electronic instruments. The mechanical ones, the ones that I already gave some examples of, These are very reliable for static and stable conditions, but their disadvantage is that they are unable to respond rapidly to measurements of dynamic and transient conditions. Again, one example, if you go back to those speedometer or voltmeters, if you have a AC system that rapidly is, transitioning between a positive and negative voltage or zero and a voltage pulsating DC, a mechanical system is too slow to follow that. So it's going to just vibrate around zero. But a digital system can, because it is measuring thousands of times per second. And according to the Shannon theory, if it's only half the frequency, you can measure anything that you want. So one thing is they are slow. They are cheap and reliable for some cases, but again, they have a limited range, and that's another problem. And they are prone to mechanical, shocks and failures as well, as I mentioned. Now, electrical ones, these are faster than mechanical, indicating the output are rapid than the mechanical methods, but it depends on the mechanical movement of the meters. The response time is 0.5 to 24 seconds. One example, again, the voltmeter itself is electrical because you have the mechanical system and the electrical, which is the coil and generating. One other example of these electromechanical systems could be some of these thermometers, and I will give you an example. And usually they are slow, so they have a mechanical component and the electrical system to measure voltage or current. And then we have the electronics, which are the most reliable systems that are widely used right now. It uses semiconductor devices, and weak signals can also be detected. So one good thing about these, extremely precise. A mechanical or electrical voltmeter can't measure anything below 50 millivolts or so. This could measure 1 millivolts, a few microvolts even. So even smallest movement, it could measure it. They are extremely fast. They can do thousands and thousands of measurements per second, which is 10,000 times sometimes faster than a mechanical system. And they could be built extremely from semiconductors and ICs, which can be built very, very small. But a mechanical system can't be done that way. Electronic systems can directly give digital measurements. For a mechanical system, imagine if you have a thermometer that's measuring your grill temperature, and if you want to build an automated system to turn on and off the gas, the output of that mechanical thermometer, you have to put a camera or something to measure it and convert it to digital. But if you have a digital thermometer, you can directly give that output to the control system. So integrating a IoT system, a control system to an electronics measurement system is going to be way easier. And at the end, I will give you some examples of IoT-based systems. One project that a student did last semester, I'm going to give you an example, is he built a system for these sucker rod pumps on oil. Have you seen these sucker rod pumps in the oil fields? The pumps that look like this, they have like a hammer type, and these are actually the sucker rod pumps. They call this sucker rod pumps. So now these systems, they have a weight on one side, and you have the motor. And the problem is, so oil has a higher viscosity than water, and some of these wells, the older wells, for every 100 barrels that they pump, 95 barrel is water, only 5 barrel is oil. Some of them are even less. I've seen oil rigs and some wells that produce 99 barrel is water, 1 barrel is oil. So below a certain point, it doesn't even pay for the electricity to pump it out. So when the viscosity is higher, meaning it's oil, the motor is under pressure. When the motor is under pressure, it draws more current from the system, okay? So if you put an ammeter on this motor, you have a motor and it's drawing power. And if you put an ammeter here, based on how much power that motor is consuming, you can determine how much oil you're pumping and how much of that is oil, how much is water. And they have a graph for it. I'm not going to go into the detail. The graph looks something like this. It's like an H graph. And if it, for example, looks like this, it means you're pumping more oil. I'm not going to go through the details. So, and Chevron or I don't know, Conoco or Exxon, or they have maybe 200-300 wells in the Permian Basin. And all of these are spread out. They're like 5-10 miles apart, some of them. And the way that they measure, for example, the amount of energy consumed or if the motor is working, is they have to drive their truck, and it's all, dirt roads. If it's raining, it's going to be very difficult. And they have to drive like 200 miles a day just to measure these manually. So one project that a student did was these have analog, the old ones have analog watt meters on these motor. He added a digital one and he connected to it to an IoT, what we call a Node MCU, or you can use a Raspberry Pi or a Arduino, and measures the current. Voltage is usually, voltage doesn't change, okay? But the current is variable, and you can measure the power and the reactive real power, all of that using the current and the difference between the voltage and the angle. So he measured that, it sends it to the cloud, and you can see it on your phone, for example, and you can determine if this pump, first of all, is it working? If the motor is working, if not, you would see that there's no current passing. And if it's working, how much oil it's producing or how much water it's producing. You can determine that by the current fluctuation as well. And it gives you an estimate. And instead of driving all to these wells, you can have 100 of these connected to all your wells and see it on a dashboard on your computer. So this is one way that you can use. But the problem that he had with most of these oil rigs, these are 50, 40, 60 years old oil rigs, and they don't have watt meters on them, or they have very old, mechanical ones that measure the voltmeter using these watt meters, these mechanical watt meters. And getting that information and converting it to digital and then sending it, it's going to be difficult. But if you have electrical ones, you could just simply give the output to a Raspberry Pi and transmit that data. And it's the same thing. I had another project, a student working on these water meters. Most cities, they have these mechanical ones, and getting that data, sending it to the water company, they had to change all these water meters. I don't know if you've seen in a lot of parts of Amarillo, they came and changed every single one, because these mechanical ones, a person must come and read them. So it takes forever to read, a block or a community of water, usage. But if you change them to an electrical one, you can have all of them connected to a 5G or 4G network, and you're just sitting at the central control system and measure and seeing that. It's the same thing for electrical. All these power meters that you have at home, EXO came and changed all of them. For my home, it was like 2 years ago. They changed it and replaced it with the digital ones. So the digital ones have several benefits. The mechanical ones only measure the total amount of power, but they don't give you an exact measurement of how much power you consumed at the peak hours. But with the digital ones, they can determine how much power you consume in the peak hours, and the peak hours, usually the power price is much higher than the off-peak. And they have different ratings, power ratings. I don't know if you can participate in those. And it's good if you have an EV and you want to charge it overnight, or you do your laundries, in the off-peak hours. But if you're using your majority of power between 6 and 9 p.m., it's like 5 times the price, 4, I think, or 5 times the price. But at the off-peak, it's like 4 cents, I think, per kilowatt hour. And I don't know the latest. And the thing is, they change the numbers in winter and summer as well. So in summer, it's a little, sometimes some places cheaper. So different seasons, different times, they can give different rates with those digital ones. I think it's enough up to this point. We're going to have a small Kahoot quiz so you can get familiar with how the quiz are going to be as well. Just give me 1 second too. And this is it for the online students. For the online students, I would post the exam for them on the website. Thank you.